So, let me state what is Fano's inequality first. Okay. So, this discussion I have taken from Robert Ashe. Okay. So, the notation is slightly different, more or less same, but slightly different. So, instead of using 2 raised power nr in the beginning, he is using letter S for the size of the code book. So, Sn is the code, second letter means the same thing, n long code words, and how many of them? S. And the code words are denoted by x1 to xs. Okay. So, x1 is the first code word, x superscript s is this is his notation. So, a typical code word, one of these will be denoted by x, and these are the n letters x1 to xn. Okay. And this code word will be this is equal to xi, the ith code word out of these s, and you put a uniform distribution on this code book of size s. So, with probability 1 over s you pick up ith code word. Okay, that is a special case, but here Ashe is offering a more general result. So, instead of specifying uniform distribution, he says let us take an arbitrary distribution. So, xi with probability, later we will come to uniform distribution pxi. So, with probability pxi, ith code word is picked up for transmission, and sum of these probabilities is equal to 1. Okay. So, it is good to have a statement slightly more general than what could be otherwise. So, this is our context, Sn code, meaning S is the number of code words and N is the length of a typical code word. Probability with which you pick up ith code word is pxi, which add up to 1. Okay. P is the probability of error by definition. Okay. So, with this notation, the statement is Fano's inequality says that Hx given y, the uncertainty regarding input given the output is less than or equal to h pe comma 1 minus pe. So, this is a distribution on 2-point set. Pe is the probability of making an error and 1 minus pe is the probability of not making an error. So, everybody knows that this is between 0 and 1, because if entropy is computed on base 2 and maximum value of this is 1, and p typically will be small. So, this will be close, this will be small, but it is a function of the distribution p comma 1 minus p plus p times log of s minus 1, where s is the size of the code book, right. This is the statement of Fano's inequality. For a moment, before we get to the proof, let us focus on the statement itself. If I plug in P equal to 0, yes?
S1 is totally under the law, right?
Yeah. Oh, okay. That's right. Okay, that was a parenthesis, yeah. If P is equal to 0, then this term is 0 and this is also 0, right? Which means that if h of x given y, the entropy or the uncertainty regarding x after output has been observed is greater than 0, then Pe cannot be equal to 0, because the moment we plug in P equal to 0, right hand side becomes 0, but right hand side is an upper bound on this, or rather this is a lower bound on Pe. So, this can be interpreted as if this is a lower bound on Pe, or in terms of Pe this is an upper bound on this, right. So, this will be the situation for most channels h of x given y, that is for most of the channels there will be some uncertainty regarding the input given y is observed. So, that means there will be some probability of error. So, there is a lower bound on this probability of error. Okay. That is the interpretation you are going to use. Okay. So, this means that if I take h of x given y greater than 0, this implies that P e is not equal to 0, that is P e is greater than 0, okay, because there is the lower bound. And in terms of this lower bound, I can compute the minimum value of P e from this, minimum possible. So, proof goes like this. Let us look at the uncertainty of x, the input, given a specific value of the output, that is capital Y has taken value small y. This quantity can be written as h of q 1 minus q plus q times h of 1 plus 1 minus q times h of q1 to qs minus 1. First, let me define these q's. Q is probability of x being equal to g y given y equal to y, and Q I is equal to P x I divided by summation P x I given y summation P x I given y x I not equal to g y. Okay. Let me explain. Y is observed and it is decoded, the output y is decoded as gy, right. And suppose, because this is a deterministic map, a given output we have to assign, we have to make a decision as to what input is transmitted. So, gy is the decision made. This gy could be wrong or could be right. So, the transmitted word equal to the decoded thing for a given observed y, if that is, so y is observed and probability of the input that was transmitted is equal to the decoded value, that means there is no error. So, q is the probability of not making an error, right. Okay. The decoded value is same as the transmitted value, and 1 minus q is the probability of making an error. But once an error is made, error can be made in one of the s minus 1 directions. Okay. The code word, the specific code word that was transmitted, but for all other code words, if that is you can decode it other than that one, and there are s minus 1 possibilities left. So, corresponding conditional probabilities are these. Okay. So, these probabilities define this distribution, okay, and this distribution comes into play with this probability, okay, and this distribution comes into play with this probability, that is when correct decision has been made, whose probability is q, no error is made. So, that is why you have h of 1, okay, because there is only one correct decision and h of 1 is 0, okay. The entropy associated with a probability which is equal to 1 or 0 is 0. So, h of 1 is 0, okay. So, you have these three terms and this is 0. So, basically you have two terms, this term and that term. This follows from the grouping axiom. In other words, you have grouping axiom was one axiom which was used by Shannon to arrive at the definition of entropy. Many authors proceed through some other way. That was one set of axioms Shannon adopted, and the axiomatic development of Shannon's measure of information or uncertainty itself went through active research for some 25 years from 1948. So, a lot of that effort has been documented in the book by Axel and Deroxy 1975. Okay. In Robert Ash's book, that Shannon's approach is documented in first chapter, the axiomatic development. Unfortunately, it is not given in Cover and Thomas, although it is pretty much a graduate level textbook. So, I teach always the axiomatic development of Shannon's entropy, and the first chapter of Robert Ash is beautiful. And there is another development given in one of the exercises in Ash's book. Okay, so grouping axiom tells me that that this much uncertainty is removed the first stage. After that, on the average, this much uncertainty is left at the second stage. So this equality is a direct application of grouping axiom. Okay. So this is the first step towards the proof. But I am making a statement here on the average uncertainty of x given y, and this is the average uncertainty regarding x given a specific value of y. Therefore, I need to take the average of this with respect to the distribution of y to get here. Okay. So this is where I will need to erase the top part to create space. If I take the average of this, both sides, that is, I multiply by the distribution of y, whatever it is, and carry out the sum, that will be giving the average. So h x y given y is equal to summation p y h x given y equal to y, the average of this over all possible values of y. Okay. That will be equal to, so far we have equality here, but here we have inequality. So we will see in a moment how inequality is arising. Right now we have equality. Okay. So this will be the average with respect to the distribution of this uncertainty. So let me be little more explicit. P E given y, probability of making an error given y is observed, comma 1 minus probability of making an error, that is probability of not making an error while y is observed. That is what, this is my q and this is my p. Okay, this p over possible values of y. This is 0 anyway, so I ignore it. Okay, and 1 minus q. This is 1 minus q is the probability of making an error, because when you do not make an error, this term arrives, and when you make an error, this term, this is a probability. So this is probability of making an error. So P E given y times this. Okay. Now, by the way, on this I will plug in an upper bound. This is distribution on s minus 1 point set, and the maximum value of that is log s minus 1. That will be the case when all these are equal, right. So if I plug it in, then this is equality, all right. I can write it like this, and write, instead of writing like this, so P y you have, and multiply by the upper bound log s minus 1. So this term has been replaced before the average itself by log s minus 1, which is an upper bound irrespective of this distribution. Okay, and this becomes PE. So this is equal to PE. Okay, by definition. This is the conditional average of, that is the average of the conditional probabilities. So that becomes the overall probability of error. And what about this? This, as a matter of fact, is less than or equal to h of PE 1 minus PE. This is the case, and the second term is PE times log s minus 1. I am copying it as it is. How does this follow? That this sum, this weighted sum is less than or equal to this. This follows from concavity of h. PE given y, comma 1 minus PE given y defines a distribution on 2-point set. So when I take the average of these entropies with individual distributions over all possible values of y, right, the overall average distribution that will be induced will be this. So h computed for this overall average distribution actually is an upper bound on the average of those entropies. But that follows from the description. For 2-point set, you know, the h, when you plotted it, goes through a maximum concavity. Okay, so that phenomena, concavity of h, has been exploited over here. So this has been replaced by this, and I have an upper bound. and on this I have already used this upper bound, and this becomes equal to that, and this is the statement of, this was the term in the Farmer's inequality. Okay. So, grouping axiom along with the simple observations that yes, uniform distribution maximizes this, and then take the average, and concavity of H gives me Farmer's inequality. Any questions here? These are very simple things that we have learned and we have just applied them. But the interpretation of Farmer's inequality also is possible, as I just gave you, that if H x given y is positive, then P e cannot be 0, right. Right hand side is an expression depending on P e, and that expression becomes 0 if P e is plugged in to be 0, which cannot be the case if H of x given y is non-zero. So, this statement will be used to complete the proof of the converse of Shannon's coding theorem. Okay. So, I shall erase everything now. This is the statement, so maybe I can leave it as it is. So, this is the statement of Farmer's inequality, and let me erase the details. Okay. We will make use of that. So, before I make use of that, there is another simple statement that I should prove, a lemma, which says that for a memoryless channel, by the way, in this actually explicit reference to the nature of the channel was not made in Farmer's inequality. Memoryless assumption was not needed. So, its applicability is much wider, okay. Because you may be interested in proving the converse to a channel coding theorem for a greater variety of channels. So, at all those places this inequality will be usable. So, for a memoryless channel now, with input x1 to xn, these n inputs, and corresponding outputs, output y1 to yn. What we are saying is that I x1 n, I can put a comma over here. Which notation have you seen? You can put a semicolon if you like, or comma, or you can put this slanted bar which Ash uses, it does not matter actually. The moment I use I, then I am talking about mutual information, whether I put semicolon. Okay. So, let me just use a comma, okay, because it is symmetric anyway in both the variables. So, this quantity is less than or equal to I x I. Actually, why do not I use Ash's notation? He uses this. Although this kind of slant bar makes greater sense for conditional entropy. Okay. So, do not let it bother you. I refers to mutual information. So, I x given y is same as y given x. You know that symmetry because it is I. This statement. So, the information carried by y about x or vice versa for n letters is less than or equal to sum of the information carried by individual letters. That is what it says, provided the channel is memoryless. By the way, the source, the symbols are not assumed to be memoryless. Okay. So, it is a reasonably general result. Only memoryless nature of the channel will be used. How do we prove that? Look at the conditional entropy of these n output letters given the input letters. Okay. This can be written as summation p x1 n. This is a compact notation for n long sequence starting from 1 ending at n, y1 n. So, this is the input sequence of length n, output sequence of length n, and the joint probability. So, that is what it is. let us try to understand this expression. This is where I have made use of the memoryless nature of the channel, that the channel operates on input symbols individually. Therefore, y1 to yn is produced as the output, and in that production only the of ith output letter, only the ith input letter comes into picture, although the input letters may not be independent of each other. That is all right. Okay. That is the part that has been used. Okay. Since we are talking about, and there will be a okay, I am missing a minus sign here, right, because this is log of sum of the logs is same as log of the product. So, this is log of this product n, okay, and I am talking about uncertainty. So, in the computational uncertainty there is a minus sign, right. So, these conditional probabilities, that is expectation of this, once I compute the expectation I will have to make use of the joint distribution, okay. That is clear, because this is a function of the joint distribution. That is why I multiply this by these properties and carry out the sum over all possible pair of input output sequences. Okay. What is the expectation of a single term? This is h of yi given xi, because all other letters will not come into picture because they will integrate to 1, right. So, only the distribution of xi yi will come into picture for computing the expectation of ith term, and that will give rise to h of yi given x. So, this becomes okay. This is a little exercise for you to convince yourself. What we are doing is we are just taking this expectation, we are computing the expectation for individual terms and then adding. In other words, we are taking the inner sum outside, that is all we are doing. Okay. So, some of these conditional uncertainties of individual letters actually becomes the expression, exact expression for this. This is happening because of the memoryless nature of the channel, where the memory, whether it is there in the input letters or not, that does not come into picture. Okay. So, having arrived at this equality, I can now write the expression for this mutual information. I know there are two possible expressions. I can use x first and y later or vice versa. So, let me use y first, that is I look at the, although it, so it is the difference of two uncertainties, unconditional minus the conditional. For unconditional I can use y, and for conditioning x, or vice versa. I will use x for conditioning for the simple reason that x is serving as the input. Okay. So, this minus h of y1 to yn given x1 to xn, okay, that quantity, which is equal to this, and this uncertainty is less than or equal to sum of the individual uncertainties in general, because those yi's need not be independent, right, because xi's are not independent. If xi's were independent, then yi's will also be independent, but I am not assuming that. Therefore, uncertainty associated with n long output sequences is less than or equal to sum of the uncertainty associated with individual letters. So, this quantity is, I will plug in the inequality, the upper bound on this, which is summation h yi 1 to n, clear. This is the upper bound on this, and for this I have this equality. So, minus summation h yi given xi. Now, I will combine ith term here with ith term here, and the difference of the two is the information given by xi about yi. So, this is equal to summation I xi given yi 1 to n, okay, this. So, the independence of x was not required. Memoryless nature of the channel we used to arrive at this inequality. This will be another result which we will be using. Now we are ready to complete the proof of weak converse, these two results, Fano's inequality and this particular result. Since we have seen the proof and Fano's inequality is also sitting in front, let me remove the proof part, unless there is a question. Is there a question? It was simple analysis. This was equal to this, and I computed the expectation of individuals, and then I noticed that individual is this, and that's it. Okay, because I'll make it as a conditional distribution of y given x to come, and then compute it, and then take the expectation with respect to x. So that will give me this. Okay, I'll do it for each individual. That is how I'll arrive at here. So I'm just saving one line while explaining that, and then I just use this expression and use the fact that this is less than or equal to this, and this is precisely equal to this. Combine this with this, that becomes this. So, okay, these 2-3 steps get me to this statement. Shall I erase the proof now? Okay, the proof is going now. And this is my Fano's inequality. So there is a distance and it looks funny. I think let me write here, and so that I can erase from here. Okay. So these two statements we have proved. Okay. This is Fano's inequality. To complete the proof of weak converse, these two statements I did. The final statement that I want to make, let us call it a lemma or weak converse. It says that log s, s is the size of the code book, that is the number of code words. So log s, if the size of the code book is 2s power nr, then log s becomes log of that is nr. Okay. So log s is less than or equal to nc plus log 2 divided by 1 minus pe bar. Pe bar is the expression for pe when all the input words are equally likely. That is a special assumption, which I did not make use of so far, because I worked with arbitrary input distribution. So P bar is not the result of arbitrary distribution; it is the result of uniform distribution on the code book. Okay. You please write it in your notes. What is P bar? Okay. Let us understand the ramification of this, and then we will get to the proof. This is basically the statement of weak converse. Suppose my S is greater than or equal to 2 raised power n C plus delta. C is the capacity of the channel. Okay. So suppose I choose S, the size of the codebook S, to be of this form, which means the exponent was R, so this is my R. R is greater than C. That is, I am trying to transmit at a rate greater than the capacity, right. So if S is indeed chosen to be like this, and this inequality which we are going to prove will mean that log of S, so this means we will have log of S is that is n times C plus delta, that is log of S is less than or equal to NC plus log 2 over 1 minus PE bar. Okay. Take 1 minus PE bar over here and bring it over here. So 1 minus PE bar is less than or equal to NC plus log 2 divided by n c plus delta. Okay. Divide by n both sides. So, this is c plus log 2 over n divided by c plus delta. Log 2 over n can be made arbitrarily small as n becomes large, but I know that delta is strictly greater than, so this number becomes strictly less than 1. That means probability of making a correct decision is strictly less than 1. That means P e bar is strictly greater than 0. Okay. So, this means P e bar is greater than some epsilon. You can compute that epsilon. Okay. It is bounded away from 0. This is happening because if you are trying to transmit at a rate greater than the capacity. So, you have chosen a rate r which is equal to c plus delta, no matter how small delta is. For large n, actually probability of error will become less. Now, you may wonder, well, for large n probability of error will stay away from 0, for small n it might not. Okay. So, this is a beautiful statement made in Covenant-Thomas, that if there is a small n for which the probability of error is 0, then I can use that small n and concatenate code words based on small n and view it as a code book for larger n, and that will violate this statement. Therefore, it is not possible even for small n, okay, such a thing to happen, because if we assume that, that will lead to a contradiction, because if it is possible for small n, then it will be possible by using the same code book repeatedly and being viewed as a code book for larger n, and you have violated the inequality. So, that is not possible. Okay. So, only 10 minutes are required to complete this proof, but you have seen the consequences of that. So, Farmer's inequality was telling that if conditional uncertainty of x given y is greater than 0, then probability of error cannot be, and that is what we are going to make. And the final statement is this, whose interpretation for rate greater than capacity turns out to be that P e bar is indeed greater than 0. Therefore, the average probability of error is greater than 0, that means maximum probability of error is greater than 0. Right? Shannon's direct half told us that the maximum probability of error is going to 0, and here we have a statement average probability of error stays away from 0. So, it cannot be made arbitrarily small if r is chosen to be greater than c. In other words, reliable transmission is not possible. So, this is weak converse. There is a strong converse also. By the way, strong converse does not hold for all channels. In one of the later chapters in Ash, there are results on strong converse, and one of the researchers in mathematics, Wolfowitz, who was a professor at Columbia, and Robert Ashe did his PhD at Columbia in around 1960, and in 1965 he wrote this book. So, he was very young, probably 35 or less than 35. Okay, so rarely one is able to write a beautiful book by that age, which will be read even 50 years down the line. Okay, so it is such a beautiful thing, and Ashe kept writing books. He got into the habit of writing books, one after another, probability, stochastic process, algebra, topology, this, that. Okay. So, I use his book for information theory as well as probability theory and stochastic process. That is my first preference always. So, let us complete the proof of this weak converse. Okay. Shall I retain this? If I remove it, it will be easier for me, I will have some space. Okay. It is all very simple stuff that I am erasing. So, P bar refers to P xi equal to 1 over s, that is the uniform distribution on the code book. Okay. So, first statement that we want to appreciate is Ixy, the mutual information between the input word and the output word, x extends to input word, and y, so x is not input letter, x input word actually. So now that I have put uniform distribution on the input words, with this distribution the uncertainty associated with x is log s. Okay. So Ixy is equal to hx minus hx given y, but hx itself is log s minus hx given y. That is first statement, trivial statement, right? Second statement is this, let me copy it here. I x y, by x y here actually I mean this and this. I have this less than or equal to summation I xi yi. Second statement, which we had proved earlier, right? This is proved long time ago, this is proved today, and Farnose inequality is proved today, which is this, that is also coming in. Okay. So the expression for mutual information, which is Ixy, so log s minus hxy, hx given y, this, which is the expression for Ixy, which is less than or equal to this, okay, and individually this is less than or equal to c. So this is less than or equal to nc, okay. So this is less than or equal to n times the capacity, third statement, okay. And the fourth statement is Farnose inequality. I will modify this fourth statement, this is my fourth, and to this form, an upper bound on this is 1 when both are equally likely, right. So log 2 is the upper bound on that. So log 2 plus Pe bar log s, s minus 1 has been replaced by s because s minus 1 looks funny. So I replace this by upper bound, this also by its upper bound, which is this, okay. And Pe was the average error, which now becomes Pe bar under uniform distribution, okay. You get the point. So Farnose inequality has been translated to this more simpler form in this context. This is my 4 prime. That's it. Combine these statements, okay, and you get here. So that's an exercise for you. Okay. I don't have to really do the rest. Just play with these statements to get this. To statement number 5, call it 5. Simple substitution. See, log s minus hxy is less than or equal to nc. That means log s is less than or equal to nc plus hxy, and hxy itself is less than or equal to log 2 plus this thing. So take this on this side, so you get log s is less than or equal to hxy plus nc, okay, and on hxy itself I have this upper bound. So let me do that. So log s is less than or equal to hx given y plus nc, which is number 3 translated on hxy through Farnose inequality, which is now this, is less than or equal to log 2 plus Pe bar log s, okay. Take this term on this side, so you will have log s times 1 minus Pe bar, okay. Okay, on this I have this upper bound and nc is there plus nc. So nc plus log 2 divided by this, that's all. So we are done. This is called weak converse. Weak converse only tells me that the probability of error, if you try to transmit at a rate greater than the capacity, stays away from 0, bound to stay away from 0 for large n. Direct half told me that probability of error can be made arbitrarily small. So, reliable transmission is not possible for r greater than 0, because probability of error cannot be made arbitrarily small. For r less than c, no matter how small is the difference, it is always possible to choose an n large enough and come up with an encoding scheme in principle. Closer the value of r to c, larger will be the value of n required, which will add to the complexity of the design process, design of codes as well as decoding. Okay. So, I do want to restate the fact that there are channels for which strong converse holds, and for these channels, memoryless channels, okay, strong converse holds. So, Ash gives a comment on that. I do not think Covenant Thomas in anywhere gave a comment on strong converse. So, Covenant Thomas is a book which is more user friendly. It is updated, but there are very deep statements made in Ash which other authors have shied away from later. And the text becomes more student friendly. So, I use a combination of the two. Certain topics I take from Ash and certain topics I take from Covenant Thomas. So, if you want to go deeper into coding theorems, then look at the book by Wolfowitz, Jacob Wolfowitz, who was a professor at Columbia. Coding Theorems in Information Theory, that is the title. So, there are two editions. I think the first edition appeared in 60s and second around 70 or around 1970. So, coding theorems you might be able to download from net by Wolfowitz, and I am sure Robert Ash as a student would have done a course with Wolfowitz. So, now we can take up questions. You can ask questions related to today's discussion or the discussion of previous 2 lectures. My last lecture will be tomorrow, 1.5 hours at 3 p.m. on rate distortion theory, where I will be computing the rate distortion function, that is the lossy representation, rate distortion function of Gaussian source, memoryless time discrete Gaussian source and time discrete binary source. And beautiful information theoretic arguments will be used to arrive at the expressions, no optimization techniques. 1. So, that will be like half an hour, maybe 40 minutes, and some comments on those. Then I will prove rate distortion theorem, and the proof of rate distortion theorem requires as much effort as the proof of channel coding theorem, and then the converse of the rate distortion theorem. So, okay. So, all that may not be possible in 1.5 hours, it might take little more than that. So, any questions? No difference, no difference, yeah. Mean, average, expected value, ensemble average, they all mean the same thing. If you by mean, if you use a qualifier in front of that sample mean, then that is a different thing, that is a random variable. So, mean, average, ensemble average, expected, they all mean the same thing.
So, if I have to explain joint difficulty to someone who doesn't understand math at all,
Weak law of large numbers you have to make use of. So, you just prove weak law of large numbers for him using Chebyshev's inequality where it is applicable, because weak law of large numbers, the simple proof of that makes use of Chebyshev's inequality. Chebyshev's inequality will call for the way you have seen, will call for the existence of second moment, that is the variance, etc. Whereas law of large numbers requires only the existence of first moment. So, there are situations where the first moment exists and the second moment does not exist. That means Chebyshev's inequality will not be applicable, but it does not mean that weak law of large numbers does not apply. Strong law of large numbers applies as long as ensemble average is well defined, the expected value, right. Only thing is, then weak law of large numbers itself will take more effort. So, some proof of weak law of large numbers, okay, and then use it. That is how you will explain. You cannot dispense with weak law of large numbers. That is taught to our students in second year course on probability instances, weak law of large numbers. Yes. repeat your question so that I get the full meaning. Just repeat.
Suppose that I have to tell somebody about compression. Why we need compression from A to A.
Yes.
So without telling them to asymptotic equivalence.
Without referring to asymptotic equipartition property. Still you want to illustrate through some example how compression is taking place. Okay. First thing is refer to a periodic sequence. Try to indicate that periodic sequences do not carry any information asymptotically. The information rate is 0 asymptotic. Whatever information is carried by a sequence 0, 1, 0, 1 is carried by first 2 digits, then the pattern repeats itself. After that, if there is any information, it is just in that n, the length of the sequence. Okay. So, if you say that n times repetition of that in a finite length sequence of a given pattern, you have conveyed the information. Okay. So, to convey that information, you will give the initial pattern for a periodic sequence and you will tell how many times it is repeating itself. To encode a given integer n, you require like roughly log n bits, and to convey a small pattern, it requires some constant number of bits. Therefore, some constant plus log n roughly is the number of bits required to convey a periodic sequence. If you divide it by n, the ratio goes to 0. So, a very simple encoding scheme is demonstrated through this example that periodic sequences and the information rate is without referring to probability at all. Okay. You can try to give Lempel's algorithm that both LZ77 and LZ78 they work outside probability context. Outside probability context, LZ77 is optimal was proved in 99 and LZ78 was proved to be optimal in 78 itself. So, you just tell that what is happening over here is that a pattern that has been seen earlier or a piece of information that has been seen earlier, you will make a reference to that. That is the basic act that is taking place, referencing. That is how compression is being achieved. So, the information or the effort involved in is giving the reference to where it is sitting is less. Specifying the location requires less effort, and it is an optimal thing to do that has been established by mathematicians. So, Lempel's algorithms provide enough incentive for discussion if you want to show how compression is taking place, because when you will look at a sequence of zeros and ones or a sequence of letters A, B, C, D, etc. of a typical text, you will show that if I do this exercise, see what is happening. And you might be able to construct a sequence of letters or sequence of zeros and ones of say length 50 and might be able to demonstrate that compression is taking place. So, the person will be happy. Okay. For a small sequence that will not happen. 10 long sequence might get converted into 20 long, but 100 long sequence might be converted into 75 long sequence. Okay. So, to make the person happier, young boy or girl happier, you tell the person that okay, write a small program and run it on different files and see the outcome. Okay. So, what we learned, that example is the best form of teaching. So, you will demonstrate the applicability of something, an idea, an algorithm through examples first. Professor Zev in 2009, 1969 at the age of 78 returns to that problem of LZ77 and proves the essential optimality. So, introduces yet another criteria of optimality and proves the essential optimality of that, a small paper, 5-page paper in transactions, which one of my students presented as a term paper also. Okay. In other words, there is certain kind of optimality, more powerful statement on optimality which holds for LZ77, but it does not hold for LZ78. So, since we have a few minutes left, rate of convergence, how fast these are algorithms, because they do not assume the knowledge of the distribution. So, that has to be picked up. So, obviously, these algorithms will not compress as fast as Huffman algorithm, because Huffman algorithm assumes more, right. So, asymptotically what happens is in LZ78 the compression ratio goes to that is the redundancy goes to 0 at the rate of 1 over log n. As n, the length of the sequence goes to infinity, 1 over log n. So that means the redundancy that you introduce in the process of encoding is of the order of some constant times, C n over log n. C is some constant n over log n. So entropy rate, let us say, is positive. That means n long sequence has been compressed to roughly nh long sequence, right? And asymptotically, the second term is negligible compared to the first term, but it is not negligible compared to the first term, but it is still going to infinity. So second term is of the order of n over log n. So per sample redundancy is 1 over log n, which is going to 0. Okay, that is the price you pay. In LZ77, 1 over log n W rate we established in 2016 for a minor modification of LZ77. Okay, so we shall stop here. Thank you.